Now I continue to read the book by Greene, Until the End of Time. Last time I read some parts of the first chapter. I think I need to repeat some of them, but it is mainly about energy and entropy. Okay. The discussion might lead you to think that the first and the second laws are thoroughly distinct. After all, one focuses on energy and its conservation, the other on entropy and its growth. But there is a deep connection between them, highlighting a fact implicit in the second law that we will return to repeatedly. All energy is not created equal. Consider, as an example, a stick of dynamite. Because all of the energy stored in the dynamite is contained in a tight, compact, orderly chemical package, the energy is easy to harness. Place the dynamite where you want its energy deposited and light the fuse. That's it. Post-explosion, all of the dynamite's energy still exists. That's the first law in action. But because the dynamite's energy has been transformed into the rapid and chaotic motion of widely dispersed particles, harnessing the energy is now extremely difficult. So, although the total amount of energy doesn't change, the character of the energy does. Before the explosion, we say that the dynamite's energy is a high quality. It's concentrated and easy to access. After the explosion, we say that the energy is low quality. It's spread out and difficult to utilize. And since the exploding dynamite fully abides by the second law, going from order to disorder, from low entropy to high entropy, we associate low entropy with high quality energy and high entropy with low quality energy. Yes, I know, it's a lot of highs and lows to keep track of, but the conclusion is a pity. Whereas the first law of thermodynamics declares that the quantity of energy is conserved over time, the second law declares that the quality of that energy deteriorates over time. Why then is the future different from the past? The answer is, apparently from what we have now developed, is that the energy powering the future is of a lower quality than that powering the past. The future has a higher entropy than the past, or at least that's what Boltzmann proposed. Boltzmann and the Big Bang. Boltzmann was surely onto something, but there is a subtle clarification to the second law whose implications, truth be told, took some time even for Boltzmann to appreciate fully. The second law is not a law in the traditional sense. The second law does not absolutely preclude entropy from decreasing. It declares only that such a decrease is unlikely. For the pennies, we have quantified this. Compared with the soul configuration with all heads, it is 100 billion times more likely that a random shaking will yield a configuration with 50 heads and 50 tails. Shake that high entropy configuration again, and getting a lower entropy configuration such as all heads is not forbidden, but because of the highly skilled us in practice, it doesn't happen. For an everyday physical system made from far more than 100 constituents, the odds against entropy decreasing become all the more daunting. As bread bakes it releases billions upon billions of molecules, configurations in which those molecules spread throughout your home are spectacularly more numerous than those in which they configurations in which those molecules spread throughout your home are spectacularly more numerous than those in which they collectively stream back toward the oven. Through their random jostling and bumping, the molecules could retrace their steps, find their way back to the loaf, fully onto the cooking process, and leave you with a mold of a cold raw dough. But the odds of that happening are closer to zero than the likelihood of splattering paint on a canvas and replicating the Mona Lisa. Even so, the point is that were such an entropy reversing process to happen, it would not contravene the laws of physics. While spectacularly unlikely, the laws of physics do allow entropy to go down. Don't get me wrong, I'm not bringing this up to suggest we might one day uncook bread, or witness a car uncrash, or see a document unburn. Instead, I'm stressing an important point of a principle. I explained earlier that the laws of physics put a future and a past on equal footing. The laws thus ensure that physical processes that unfold in one temporal sequence can unfold in reverse. And since those very same laws govern everything, including the physical processes responsible for how entropy changes over time, it would indeed be curious, erroneous, really, to find that those laws only allow entropy to increase. They don't. All the entropically increasing processes you have experienced day in and day out during your entire life, from the mundane of a shattering glass to the profound of a bodily aging, can happen in reverse. Entropy can decrease. It's just ridiculously unlikely. So where does this leave our quest to explain why the future is different from the past? Well, given a configuration today of a less than maximum entropy, the second law shows that the future is overwhelmingly likely to be different because entropy is overwhelmingly likely to increase. Configurations of a matter that have less than the maximum possible entropy are chopping at a bit to proceed to higher entropy. And with that observation, some exploring the difference between past and future rest easy, reckoning that their work is done. But the work is not done. Just as importantly, we need to explain how it is that we find ourselves today in such a special, unlikely, surprising state of less than maximum entropy, a universe replete with orderly structures from planets and stars to peacocks and people. Had that not been the case, had today's configuration been the expected, ordinary, unsurprising state of maximum entropy, then with great odds, the universe would continue to inhabit such a state, yielding a future no different from the past. Like the bag of pennies jostling through the enormous number of configurations with roughly 50 heads and 50 tails, the universe would relentlessly meander through the enormous landscape of its highest entropy configurations. Widely dispersed particles streaming this way and that across space, a cosmic version of your uniformly steam-filled bathroom. Today's state of less than maximum entropy is, luckily for us, far more interesting. It provides the opportunity for particles to join into structures and for macroscopic change to occur. And so we are led to ask, how did today's less than maximum entropy state come to be? Dutifully following the second law, we conclude that today's state derives from yesterday's even lower entropy state, and that state we envision derives from the day before yesterday's still lower entropy state, and so on, yielding a trail of ever-decreasing entropy, taking us ever farther back in time until we finally reach the Big Bang, a highly ordered, exceedingly low entropy starting point at the Big Bang is why today's universe is not entropically maxed out, allowing for an eventful future that differs from the past. Can we go further and explain why the beginning of the universe was so ordered? We will come back to this question in the next chapter, where we will explore cosmological theorizing. For now, we note that our survival requires order. From our internal molecular organization, supporting a wealth of life-sustaining functions, to the food sources that provide us with high-quality energy, to the crafted tools and habitats that are essential for our continued existence. Without an environment chock full of low-entropy ordered structures, we humans would not be here to notice. Next section. Heat and entropy. I began this chapter with Bertrand Russell lamenting a universe subject to relentless decline, with the second law's declaration of a rising entropy. Think of a rising entropy as an increasing disorder, and you have the gist of it. But to fully appreciate the future challenges that will face life, mind, and matter, a theme we will amply explore in subsequent chapters, we need to establish a link between the modern description of the second law of thermodynamics, as I have laid it out, and the original formulation developed in the mid-1800s. In that earlier version, the second law codified what was obvious to anyone working with steam engines. The process of burning fuel to run a machine always produces heat and waste, degradation. However, as the earlier version made no mention of counting configurations of particles and made no use of probabilistic reasoning, it might seem a world away from the statistical statement of entropic growth that we have been developing. But there is a deep and direct connection between the two formulations, one that reveals why the steam engine's conversion of a high-quality energy into low-quality heat is illustrative of a ubiquitous degradation taking place throughout the cosmos. I will explain the link in two steps. First, let's look at the relationship between entropy and heat. Then in the next section, we will tie together heat and the statistical statement of the second law. Grab hold of a salty pan's hot handle, and it feels like heat is flowing to your hand. But does anything actually flow? There was a time long ago when scientists thought the answer was yes. They envisioned a fluid-like substance called caloric, which would flow from hotter locations to cooler ones, much like a river flows from upstream to downstream. In time, the more refined understanding of a matter's ingredients provided a different description. When you grasp the pen's handle, as fast-moving molecules collide with the slower-moving molecules in your hand, on average causing the speed of those in your hand to go up and those in the handle to go down. You sense the increased speed of the molecules in your hand as it warms. The temperature of your hand has increased. Consequently, correspondingly, the slower speed of the molecules in the handle means its temperature has decreased. What flows then is not a substance. The molecules in the handle stay in the handle, and those in your hand stay in your hand. Instead, much as information flows from one person to the next in a game of telephone, molecular agitation flows from molecules in the handle to those in your hand when you grab it. And so, whereas matter itself does not flow from handle to hand, a quality of a matter, average molecular speed does. Quality of a matter, average molecular speed does. That's what we mean by the flow of heat. The same description applies to entropy. As the temperature of your hand increases, these molecules bounce around more quickly. The range of their possible speed widens, increasing the number of attainable configurations that are pretty much look the same, and so the entropy of your hand increases too. Correspondingly, as the temperature of the handle decreases, as the molecules move slower, the range of their possible speeds narrows, decreasing the number of attainable configurations that pretty much look the same, and so the entropy of the handle decreases. Wow, entropy decreases. Yes, but this has nothing to do with rare statistical flukes like dumping a bag of pennies and getting all heads. As described in the previous section, the entropy of the hot handle will decrease every time you grab it. The simple yet vital point the thought pen illustrates is that the second law's dictum of entropy increase refers to the total entropy of a complete physical system, which necessarily includes everything with which the system interacts. Since your hand interacts with the pen's handle, you cannot apply the second law to the handle on its own. You must include both the handle and your hand, and to be more precise, the entire pen, the stove, the surrounding air, and so on. And a careful accounting shows that the increase in the entropy of your hand outstrips the decrease in the entropy of the handle, ensuring that the total entropy does indeed go up. So, much as with heat, there is a sense in which entropy can flow. For that pen, it flows from the handle to your hand. The handle becomes a little more ordered, and your hand becomes a little less ordered. Again, the flow is not in the form of a tangible substance that was initially in the handle and has now moved to your hand. Rather, the entropy flow denotes an interaction between the molecules in the handle and those in your hand that affects the properties of each. In this case, it changes their average speeds, their respective temperatures, and that in turn affects the entropy they each contain. As the description makes manifest, the flow of heat and the flow of entropy are intimately connected. To absorb heat is to absorb energy that is carried by random molecular motion. That energy in turn drives the receiving molecules to move more quickly or spread more widely, thus contributing to an increase in entropy. The conclusion then is that to shift entropy from here to there, heat needs to flow from here to there. And when heat flows from here to there, entropy shifts from here to there. In short, entropy rides the wave of a flowing heat. With this understanding of the interrelationship between heat and entropy, let's now revisit the second law. Heat and the second law of thermodynamics. Explaining why we experience events unfurling in one direction but not the reverse brought us to Boltzmann and his statistical version of the second law. Entropy is overwhelmingly likely to increase toward the future, making reverse run sequence in which entropy would decrease fantastically improbable. How does this relate to the earlier formulation of the second law? Inspired by the steam engine, which was phrased in terms of the relentless production of waste heat by physical systems. The connection is that the two starting points, reversibility and the steam engines, are tightly linked. The reason is that the steam engine relies on a cyclical process. A piston is thrust forward by expanding steam and is then reset to its original position, where it awaits the next thrust. The steam, too, reverts to its original volume, temperature, and pressure, as must all of an engine's vital parts, riding the engine to heat back up and thrust the piston once again. Well, none of this requires the ridiculously improbable unfolding in which every molecule finds its way back to exactly the same spot or acquires exactly the same speed as it had at the start of the previous cycle. It does require that the overall arrangement, the engine's macrostate, returns to the same form to initiate each subsequent cycle. What does that imply for entropy? Well, since entropy is a count of the macroscopic configurations that present as the same macrostate, if the macrostate of the steam engine is reset at the start of each new cycle, then its entropy must be reset too, which means that the entropy the steam engine acquires during a given cycle, as it absorbs heat from the burning fuel, as it generates additional heat through friction of its moving parts, and so on, must all be expelled to the environment by the time the cycle concludes. How does the steam engine accomplish this? Well, we have seen that to transfer entropy, you must transfer heat. Thus, for the steam engine to reset itself for the next cycle, it must release heat into the environment. That's the historical statement of the second law of thermodynamics. The inevitable expunging of waste heat into the environment, the very degradation that so weighed on Bertrand Russell, now derived from the statistical version of the second law. This is the destination I have been heading for, so feel free to jump to the next section. But if you have the patience, there is one detail I would be remiss not to mention. You might wonder if the steam engine absorbs heat from the burning fuel, thus absorbing entropy, only to release heat to the environment, thus releasing entropy. How does it have any remaining energy to accomplish useful tasks, like powering a locomotive? The answer is that the steam engine releases less heat than it absorbs, and yet is still able to fully purge the entropy it has built up. Here's how it goes. The steam engine absorbs heat and entropy from the burning fuel and releases heat and entropy to the cooler environment. The temperature difference between the fuel and the environment is what's vital to see why. Imagine turning on two identical space heaters, one in a room that's frigid and the other in a room that is hot. In the frigid room, the cold molecules of air are jolted by the space heater, causing them to move faster and disperse widely, and so their entropy increases significantly. In the hot room, the air molecules are already moving fast and fleeting widely, and so the space heater only slightly increases their entropy. It's kind of like burning the heat at a wild New Year's party and barely noticing that the revelers dance a touch more quickly. But turn up the heat at the thickly monastery, enticing monks to break from their meditative practice and start crumbing, and you would readily see the change. So even though the two space heaters are identical, the entropy they transfer to their surroundings is different. While each generated the same amount of heat, the space heater in the cooler environment transfers more entropy. A cooler environment thus amplifies a given amount of heat received into a larger entropic increase. With the realization, we see that the steam engine can discharge all of the entropy it acquires from the hotter fuel by expelling only part of that heat to the cooler environment. The remaining heat is then available to derived in steam to expand, pushing the piston and accomplishing useful work. That's the explanation, but don't let the detail cloud the larger conclusion. Over time, physical systems will, with a fantastic likelihood, evolve from configurations of a low entropy toward configurations of a higher entropy. If a system, like a steam engine, seeks to maintain its structural integrity, it must stave off the natural drive toward increased entropy by transferring the entropy it builds up to its surroundings. To do so, the engine must release waste heat to the environment. Let me stop here.